Hi, this is Mr. Swanson, and today we're going to look at video notes 6.2 on the concept of the mole and the molar masses. So I suggest you taking the copy of the notes and following along with the video. We have to talk about the concept of the mole because atoms are really small. So in any given sample of an element, there are going to be so many atoms that it's not practical to talk about them. So we group them together in the concept of the mole. The mole is a counting unit, just like a dollar, a dozen, a day, or anything else. It just indicates how many of any given thing. So I could say a mole of an element is 6.022 times 10 to the 23rd particles, or I could say a mole of bananas is 6.02 times 10 to the 23rd bananas. And so a mole is just a counting unit to describe a large amount of a small thing. So Avogadro was a man, and there's a good TEDx video about him, who came up with this concept that many people didn't agree with at the time. And he's given credit for coming up with this number, 6.02 times 10 to the 23rd particles. And we call that the mole. And we came up with that number is essentially we had to create a standard. And so we took 12 grams of carbon, carbon 12 specifically, that isotope, and we found that there were this many particles in it. So everything's based on the idea that 1 mole of carbon weighs 12 grams and it has that many particles in it. Here's a little graphic to help you kind of picture what they are talking about. And like I said, there are a couple good videos. If you Google the mole, some TED Talks and TEDx videos, TED Education as well, have good videos on Avogadro or the mole. Now, you're going to really have to trust me on this, that we're going to show you a process that you've probably heard before called dimensional analysis. And that's going to help us solve a problem like number 1, where we're looking at how many dozen are in 120 eggs. And sometimes you're going to say, I really can do this in my head, I don't need to show your work. But you really do. And I promise to have less problems, but you have to show a lot of work on those small amounts of problems. Because as they get more difficult, showing your work is super important. Okay, so please show your work. And what you're going to do is you're going to take your known value, and this known value starts at the top. And you can see this done a little bit by different teachers and slightly different methods, but you're going to start with putting your known value up on the top. And you want to put the number and the units, so eggs is the unit. And then I like to make this train track. I think this is the better way to do it. And then so every essentially column, every 2 boxes, is what we call an equivalence factor. It's 2 things that are equal to each other. So we know that 12 eggs equals 1 dozen. And so I want to convert from eggs into dozen. So you put the unit that you want to convert to up top, and you put the unit that you want to get rid of on the bottom. Then you look up and say, okay, I know that in 1 dozen, there's 12 eggs. And so now eggs divided by eggs cancel out because anything on the top and the bottom is just 1. And so you're going to go 12 times eggs times 1 times dozen divided by 12 eggs. And it looks like I should have said 120 up there at the top, but that's okay. I caught my mistake because I was showing my work. So if you do this, eggs divided by eggs cancel. 1 you can just ignore, and 120 divided by 12 equals 10. So we have 10 dozen eggs. Okay. So see if you can pause the video and take a look at how you would do that for problem number 2. So hopefully you set it up like this, and as you're given the answer, we can apply what we learned in the previous unit. Counting units, like what you see in the second column, have unlimited sig figs. And so we're going to call this, we don't focus on that second column for sig figs. We really look at what we're starting with. And so that first one has only 1 sig fig in this. And so when we give the answer, we want to round it to 1 sig fig. So I get 2 times 10 to the negative 17th moles. So for the sake of time, let's have you practice 3 and 4, but don't bother with any of the calculations. Let's just put a generic number down and make sure you are doing the dimensional analysis correctly. So pause it and try a little bit on your own. So hopefully you set it up like this, and keep in mind, small point, but the numbers in the middle in this kind of second column, those are all those counting numbers. So you don't really consider those sig figs. So you want to look at the number of sig figs in the starting problem, which is 1. So both your answers should be in 1 sig fig. All right, so now we get to the topic of, we introduced the mole. Now we get into the topic of molar mass. And it's as simple as it sounds. It's just the mass of 1 mole. And so if you understand that there's 6.022 times 10 to the 23rd atoms in a mole, and you can figure out the mass of those, then you can calculate the mass of 1 mole. And so the units for molar mass are in grams per mole, whether it's written like that or written like grams over mole. Same thing, that indicates the molar mass of something. And so you're going to find that by using the periodic table, and especially use the periodic table that we gave, because it has the right molar masses. It's rounded to the correct amount of digits, so it won't always be the same. So here's an example that the molar mass is written on the periodic table, and you can see this one only has 1 sig fig, or 1 decimal point, and this has 2 decimal places, so ours has a standard amount in the Minnetonka version. So you're going to use that. So this means a mass of silver. 1 mole of silver weighs 107.9 grams in 1 mole. So grams per mole. However, most of the time you're going to be dealing with something more than just an element. You're going to be looking at a compound. And so to find the molar mass of a compound, it's just the individual molar masses added up. So if we have a simple example, HCl has 2 atoms in it. So their molar mass of hydrogen is 1, and chlorine is 35.45. And so you add them together to get the overall molar mass of HCl. So for the rest of this year, the most common calculation you're going to have to do is convert between grams and moles. It's very important that you can do this super accurately, and then eventually you'll get a little bit faster at it. So for now, I'm going to, skip this second step, and let's just take a look at the first example. So we have 10 grams of sodium, and we want to know how many moles it is. So take your given and put it up top. And again, do not forget the units. On the test, I need to see them. And so you want to get rid of grams, and you're looking for moles of sodium. So you're going to put moles of Na up top. And moles and grams are related via the molar mass. So there's a certain amount of grams of Na in 1 mole of Na. And you can find that from here, the periodic table. So 22.99. Now, when you do this, you're going to quickly see that grams of Na cancels with grams of Na, and you're left with moles of Na. And so then you just do the calculation, and then you're going to get a number with 3 sig figs, and the units are going to be moles of Na. And again, 3 sig figs because there's 1, 2, 3 sig figs in this one. So you're multiplying everything across the top, and then dividing by 22.9 at the bottom. And I think the number is somewhere like 0.435 moles. I think that's what you should have gotten. So let's practice counting the molar mass for this one. So take a look at hydrogen, and there's 2 of them, and oxygen. And so you look at those masses, or the molar masses on the periodic table. So you're going to take 2 hydrogen, so 2 times hydrogen, and 1 times oxygen, and you're going to add those up, and that's going to give you the molar mass. So take a second to do that. So when you do that, you get 18.02 grams in every mole of water. then you'd follow that same dimensional analysis process, and you'd have 100 grams of O2, and you want to convert it into moles, and so you have to put that 18.02 grams in 1 mole. So you're going to be using these, and you're going to end up having to flip them based on whatever you start with. If you start with grams on the top, you have to put grams on the bottom. If you start with moles on the top, you have to put moles on the bottom. So to calculate the molar mass of glucose, which is a form of sugar, you're looking at 6 times carbon, which is 12.01, plus 12 times hydrogen, which is 1.01, plus 6 times oxygen, which is 16.00, and we're getting these numbers from the periodic table, and you add that up, okay, and then you want to give me the correct molar mass. But we don't need to do the calculations right now. I'm trying to save off some time so these notes are manageable. So with that molar mass, then you can take the starting grams, and then you can get rid of grams, and you get to moles. Silver is Ag. I was thinking gold. Anyways, and you'd find this from the periodic table, so 107.87, 1 mole. And then you're going to, I think it's important that you start learning to cancel your units, so you're going to cancel grams over grams. Okay, so now we're going to go back to our first unit where we talked about moles and the ideal gas law. And so just a couple things to remember. STP means standard temperature and pressure. And so there are many units of pressure that you can use. We're going to try to stay in atmosphere on this one just to make it really easy. And we say 0 degrees Celsius as well. So if we ever use the term STP, think 0 degrees Celsius in 1 atmosphere. So Avogadro's work, he didn't really end up giving us that 6.02 times 10 to the 23rd, but what he did do was he said that at the same temperature and pressure, a mole of each gas is going to occupy that same volume. And I don't know if you remember what that volume is, but we're going to get into that. So this was really what Avogadro, this is the sentence or phrase that Avogadro is known for creating. And then they went on to get the actual numbers. So here's that magical number that he helped give us, and that a mole of gas, so this is another counting unit, a mole is going to equal 22.4 liters. So again, that's just like, 1 mole equals 6.022 times 10 to the 23rd atoms. You can also say a mole equals 22.4 liters. And because those are both equal to each other, then you can say 22.4 liters equals 6.022 times 10 to the 23rd atoms. And that's also going to be equal to the molar mass. So you can start to put all these together and make some shortcuts for math. And so we'll practice that more throughout the unit. So this is pretty much saying the same thing. This is this conversion factor that we're going to use depending on what your starting value is. I'm going to do problem 1 for you, and you can pause and try problem number 2, and you can see if it all makes sense. Okay, so I'm using this trick to kind of save time on this. So I started with the given value right here. And then I use my conversion factor over here on the second part, and I'm putting liters on the bottom because liters was on the top. And that gets me a rounded to 2 sig figs, 0.070 moles of oxygen. So problem B then says, okay, well, how many grams is that? And we could have done this all in one step, but we're breaking it up as you're learning. So then we're starting with moles, so we got to put moles of oxygen on the bottom. And because it's diatomic, the molar mass is 32 and not just 16, and then gets us rounded to 2 sig figs, this answer of 2.2 grams. And so the only thing I would have like to see then is you show canceling out these units so you really know what's going on. But I think if you get that final answer, that's pretty good. So we're going to skip that second problem because, again, so much time. And we're going to go on to one last challenging problem. So let's try to put everything together in this final problem. Pause it, try to do it yourself, and then come back to the video and see the solution worked out for you. All right, so what I did was I took, and I did this a little bit more complicated than I needed, but essentially I took 20.95% of that 6 total liters to give me how much of that is oxygen, and so we get that value right there. So the lungs are going to hold this much oxygen, and then I'm doing this dimensional analysis all in kind of one step, and so liters of oxygen are going to cancel here using the conversion factor that 1 mole has 22.4 liters. And then I'm using the molar mass right here, saying that 1 mole of O2 is this many grams, and that's the unit we're looking, and giving this number right here. So hopefully this makes sense. We can do some more practice in school. If any of these didn't, if you find an error, which definitely is possible, or if they're not making sense, screenshot them and let's talk more about them during class.